Hey everyone, in this video we're going to talk about rolling contact bearings and specifically looking at variable loading. And this video is part of a lecture series on mechanical design 2. So let's get started with this video, and we're now going to explore another type of loading condition that could happen on bearings, and that is variable loading. So we know that bearings don't always have the same loading. For example, if you're driving in a car, you have bearings that are used to attach your hubs with your wheels. And we know that there's constant variable loading in that case, and there's a random variation in that loading due to the fact that the car is not always going the same speed. And an example of this random variation would be looking at the first graph here. We have a random variation in loading. So if we think of the y-axis as how much load there is, or in what direction there is load, we can see that it's completely random and completely varying randomly. And so what we can do in order to analyze that system is we really have to analyze it piece by piece. So we try and cut it into pieces, but we can cut it into more pieces. And as you start increasing the amount of pieces, you can start analyzing each loading event and then add them up all together to try and figure out what damage you're going to have on your bearing. So the reason what we're going to do here is we're going to analyze variable loading, and then we're going to look at the effect it has on damage for the bearing and how much damage we're going to actually create by having loading. Now, the second type of loading, which is not random variation, is piecewise constant loading in a cyclic pattern. And this is one that we're really interested in because it happens a lot in manufacturing or in purposes of industry. We can have, for example, a system that would be on for 8 hours, or on at a certain loading for 8 hours, then on for another specific loading for another 8 hours, and potentially even at different speeds as well. Okay, so the loading does change. So the life and the force could change, and that would change our cyclic loading essentially. Now, this one is a piecewise constant loading. So we have constant loading, then it's on, off, and we have a repeating pattern over and over and over. And we're going to do some example problems to try and illustrate that as well throughout this video here. The third type of loading is a continuously variable but repeating pattern. So that could be a continuously variable pattern, so not a great system to analyze, but it's a little bit easier to analyze. You just repeat an integral of the force over and over and over. It's not as easy as a piecewise constant, but it is pretty easy. And what we're going to focus on is the last two, and we're really going to focus on mostly on the middle one, just to explain the concept, but you can also go into the last one as well and understand the last one in exactly the same way. The math is a little bit more complicated because you have integrals, but it's pretty much exactly the same thing. So we're going to focus on our middle one. And the first thing we can write about our system and about the analysis of our system is we can recall from previous videos the equation that says that FL to the power of 1 over A is equal to a constant. And that essentially gives us some sort of value that it gives us a value of how much force and life we can have. And the more life we have, the less force we need to have, or the more force we have to reduce the life of the bearing overall. And we can modify this equation slightly by putting everything to the power of A. So what if we were to change this equation slightly and put everything to the power of A? Okay, instead of keeping it in this format, we could say, well, we can put everything to the power of A, and we can have it as F to the power of A times L. L would just, the power of A would cancel the 1 over A, so we would just have times L, is equal to a constant to the power of A. Now, a constant to the power of A is just another constant, okay? So we can just call this K, for example, a constant K. Now, we're going to define this constant as damage. So we're going to say that the damage incurred by the bearing is equal to D. Okay, we're going to use D as damage, is equal to D which is equal to F1 to the power of A times L1, for example, if we were to choose at point 1. And we can characterize the damage that way because we know that the damage is going to be constant if F and L are modified. We know that the damage is going to be constant along a certain line. And so what we can do is we can start drawing a graph of F to the power of A versus L. Okay, so it would be F to the power of A versus L. And what we're going to find is if we plot some values here, we're going to have, for example, a 0.1 here. We're going to call this 0.1. And a little bit further down, we're going to have a 0.2. And if we actually join this graph together and add more points, we actually find that we have some sort of parabolic shape that is going to determine our damage equation. Okay, so if you look at the actual graph, the damage would be equal to the area under the curve. Okay, and we'll look at that in a second. So this is called the damage line. And if we look at the damage line and we actually look at this first point would be equivalent to the equation we wrote above. So it'd be F1 to the power of A times L1, okay? And this area in red is essentially going to characterize the damage. So if we look at the damage equation, we know that the area, so we can say that the area from L0 to L1, so we'll take L0 as life 0 or 0 life, is equal to the damage. Okay, that's based on the equation. Now, what we can also do is we can say that we could have a different point where we could move our system to F2A and L2, and that would be a different representation of that damage. Okay, but it would still be the same area under the curve. So what we can write is that D, or the damage, is going to be equal to F equivalent to the power of A times the sum of L, capital L. Okay, so if we have different damages, for example, we might have different piecewise damages. So we might be looking for a damage from 0 to 1, and then a different damage from 0 to 2, from 1 to 2, and then 2 to 3. So this equation is going to be explained in a second. So what we can say is the following. So this is the governing equation that we're going to use for now, but we're going to explain where it comes from. So what I'm going to do is I'm going to copy over a figure from our handout. So I'm going to copy over figure 1110 really quickly. And we're going to see that figure 1110 shows us a piecewise system where we have a 3-part continuous periodic loading cycle. So as you can see, we have this first loading here, then we have a second loading that's higher, and then a third loading that's here. And then we repeat the system, 1, 2, and 3. And what we're going to look at is try and develop an equation that says d FEQ to the A is multiplied by the sum of L is equal to the damage. So let's look at how we would build that up. So we see that we have different loading conditions throughout, so we need to figure out how we're going to work with these different loading conditions. Now, L is going to be the period of the slice. So it's going to be the revolutions for each slice, not the total amount. So if we write down an equation for this, we could say that the damage is going to be equal to FE1 to the power of A. And as you can see, we're using FE, which is our FE calculated from our previous video, where we could find a radial and axial. So it could be F desired, but in this case, it's going to be our Fe, which is going to include our axial force if we have any, multiplied by L1, so that would be the area under the curve Fe1 L1, so this curve right here. And then we would add to that, we would keep adding, we would figure out the damage by just adding every term and solving for the area under every curve, essentially. So we would have Fe2 to the power of A times L2 plus Fe3 to the power of A times L3, and so on and so forth. But since it's repeating, we're going to stop our analysis here. So I'll cut it off in blue here. Because it's repeating, we don't need to do it multiple times. We can just say it's repeating over and over, and the damage incurred up to 0.3 will be repeated over and over however many times we run the system. So we can simplify our equation to say that D is equal to the sum from I is equal to 1 all the way to n, so however many slices we have, multiplied by Fei to the power of A times Li. Okay, we're just generalizing the equation above, where I is equal to the slice number and Li is equal to the number of revolutions at life Li. Okay, and it'll all make sense once we start doing an example problem. But so what we can say is, based on this, we also know that our damage is going to be equal to the following equation: Feq to the power of A times the sum of life, okay? Where the sum of life is going to be equal to, so we have Feq times A, which is going to be equal to L1 plus L2 plus L3 in our case. Okay, we have these three terms put together. Now, what is Feq? Feq is the force equivalent throughout the three life terms. So it is this line right here. Okay, so what this line does right here is it tells us the average force through our whole system. It essentially gives us the average force for our whole system. And this is something we want to find, okay? We don't have the average force, but we can find it based on our mathematics and based on our piecewise approach that we have. So we can say, by rearranging the equations, we can say that Feq, okay, since damage is equal to this as well as this, okay, it's equal to those two, so we can equate those two equations. We can make them equal to each other and solve for Feq. So we can say that Feq is equal to Fe1 to the power of A times L1 plus Fe2 to the power of A times L2 plus Fe3 to the power of A times L3. So that would be the breaking down into pieces what the damage would be. And then we can divide this all by L1 plus L2 plus L3, which would be the sum of our life. And then we would do to the power of 1 over A, because we have to get rid of the power of A on Feq. And we solve that. We can say that Feq is equal to the top part. We can say that it's the sum of Fei times Li. And at the bottom, if we look at it carefully, we can say that the bottom is the sum of Li, okay? And that's all to the power of 1 over A. Okay, so we can come up with a new term that says that we can come up with a new term to group these two terms together. We can say that these two terms can also be called, so Fi, we're going to call this Fi, is the fraction of revs used under load FEI. Okay? And it might not make complete sense now, but it will make sense when we start doing an example problem. What we're essentially rewriting it as is we know that, for example, this fraction would be 1/3 of the load. This one would be 1/3 of the load. This one would be 1/3 of the load. Or you could say that L1 would be 1/2 of the load, L2 would be 1/4 of the load, and L3 would be in terms of revolutions. Okay, so it's just a way of figuring out how many revolutions out of the total are we using L1, L2, and L3 for. Okay, so it's just an easier way to annotate it, and it'll make complete sense once we start doing the example problem. So bear with me while we do this. So we can simplify this equation to the sum of Fi times FEI to the power of A, all to the power of 1 over A. Okay, and I forgot an A here at the top. Okay, so based on this, we can go a little bit further, and we can say that Li can also be expressed. If we're looking for Li and we don't have it in terms of revolutions, we can say that Li can be expressed as the following. It can be expressed as Ni times Ti. Okay, so N sub I Ti, where Ti is a time fraction or time period, and Ni is the rotational speed. Okay, so we can go and add one more thing, and then we're going to start with example problems directly so that it makes complete sense and we can work through an example problem and kind of understand how to find all the terms that we've just developed. The one last thing we need to do before we start this is add an application factor just in case. If we have some safety factor, we need to add an application factor, and that would be that we would write it as the following. So we would say that FEQ is equal, so the F equivalent for our whole system is equal to the sum of the fraction I, Fi, times AFI, which is your times FEI, which is your application factor, all to the power of A. Remember that the application factor gets associated with the force and nothing else, and then all to the power of 1 over A. Okay, so let's try and solve a problem using this technique and using this equation. Okay, this should be pretty simple to understand and should be pretty easy to practice, but we want to do 2 different example problems so that we have a clear understanding of what's happening. Okay, so let me copy over an example problem and then we'll do it in real time. So I'm going to copy this problem and talk about it on the next page. So the problem says the bearing on the output shaft of a compressor breaks, and you have no information about the manufacturer or part number of the bearing. We're told that we have to determine the equivalent radial load of a possible replacement bearing if the compressor has the following load and speed pattern. So instead of just finding an FE, which could be found if we had a constant loading, we have to actually find an FEQ for our system. Okay, and FEQ is based on the fact that we have different loads. Now we're told that we have different radial loads. Okay, we're told we have 1,000 pounds, 300 pounds, and 575 pounds as our 3 different loads. Okay, so we're given these loads and we're told they're all radial, so we assume that there's no axial loads. So our FE is basically going to be equal to our FR. Okay, and what we're going to do is we're going to make a table to solve for all the values that we need. So we know that in our question, it has a pattern that every 12 hours does the same thing. And so we're going to write that FEQ is equal to the sum of the forces in sum of Fi, which is a fraction, time fraction Fi, times AFI times FEI, all to the power of A, and that's all to the power of 1 over A. And what we're going to do is I'm going to start writing all the information that we're given in a organized table to solve the problem. I highly suggest that whenever you solve these types of problems, you do organize yourselves with a table. Okay, we'll see different levels of complexity in the problems, but this would be the easiest way to do it. So the first thing we want to do is look at the time, okay? And we're given a RPM value and a time. We're not given revolutions. So we have to write the time out and the speed out to find the time fraction, essentially. Okay, so we have a time, the time, and we're going to call this step 1, step 2, and step 3. So the time for step 1, so we'll put 1, 2, and 3 in our table. Okay, so we have 1, 2, and 3, and we're going to write the time. So time for 1 is 6 hours. Okay, it's from 12 to 6, so it's 6 hours. Then the time for 2 is 3 hours. And then the time for 3 is also 3 hours. So we're writing the overall time of the bearing operation. Now, the time is great in terms of hours, but it's not in terms of revolutions. So we also need to know the RPM. So we're going to write the speed as well during that time. So the rotational speed. And we're going to call this n sub I, okay? So the speed is n sub I. We've used that before. So for N1, it would be 1200 RPM. So I'll write the RPM here. Then we have 900 RPM. And we have 3000 RPM. The next thing we're going to write is our time fraction. And our time fraction is actually the term TI, okay? So the next term we're going to look at is time fraction. And we're going to call this T sub I. Okay? And our time period or our time fraction, so it's basically how much time we've spent overall in that specific window. And it's essentially only looking at the time factor, not time and speed, okay? So it's just to simplify and to break down our problem in the easiest way possible. So the time fraction is essentially 6 hours over 12 hours, which is going to give us 0.5. And this time fraction should add up to 1, okay? So if it doesn't add up to 1, there's a problem somewhere. This is going to be 0.25 because it's 3 over 12, and this is also going to be 0.25. Now, once we have the time fraction written down, the next term that we can write down is Li, or L sub I, okay? And L sub I is essentially the number of revolutions for each system, okay? But it's number of revolutions basically in a total form or in a fractional form, essentially. So what we're going to do is we're going to say that the Li is going to be expressed as Ni times Ti. So we're going to multiply Ni multiplied by Ti. And so life I is essentially an arbitrary number that's given to to each period to see what's the weight of each period. Okay, so in this period, we're going to have 600. It's going to be 0.5 times 1200 RPM. So it's going to be a value of 600. The next one is 3 hours at 900 RPM. So that one's going to have a much less factor. It's going to be 225. And then the final one is going to be 750. Okay, so we can see that actually the 3 hours at 3000 RPM is actually more significant to our system in terms of L sub I than the rest. Okay, then the next term we can find is F sub I, which is the fraction of the time, or the fraction of time and revolutions put together. Okay, so if you think of Li as a number that determines how much revolutions are spent at 1, 2, and 3, Fi is that fraction or that percentage of revolutions spent. Okay, so it's the percentage of revolutions that you spend in each period. Okay, and the way you can do this is you can add up all three LIs, so you can sum all the LIs. So it'd be 600 plus 225 plus 750. which is 1575. And if we go to our definition of Fi, so if we go back to what Fi was, Fi is a fraction of revs used under load Fi. So it's individual, so it's Li divided by the sum of Li. Okay, so in this case, it would be L1 over the sum of all the L's, then L2 over the sum of all the L's, and L3 over the sum of all the L's. And if we do that, we would basically have that Fi is 600 over 1575, 225 over 1575, and 750 over 1575. So we get that these values are 0.381, 0.143, and 0.476. Okay, and so now we have that value for fraction. So we have all the values for fraction. We have the F1, F2, and F3. So then we can keep going with our system, and I'm going to keep going with the table under here so that it doesn't go out of the page on the right side. But we have our system 1, 2, 3, and the last thing I want to do is write our Fe value, which is going to be, in this case, equal to Fr. And then I want to write one last value, which is going to be Af times Fe. Okay, so that we already calculate our Fe value multiplied by the application factor, because we see we have different application factor for different parts of the system. So this is 1,000 times, and then 300, and then 575. And if we go back up to the question, we see that we have an application factor of 1.1, 1.1, and 1.4. The application factor for the 3,000 RPM is probably higher because it's rotating at a faster speed. So we need to take more safety in that measure. So if we do the AF times FE, we get 1,100, we get 330 here, and we get 805. Okay, so then once we have all of this, we're then ready to be able to solve for FEQ. Okay, and FEQ is now going to be the sum of Fi times the value of AFFE to the power of A for every term. We're going to split for every term. So for part one, we need this term and we need this term, and we're going to plug them in. So we're going to have 0.381 times 1,100 to the power of 3. That would be our first term. Our second term would be 0.143 times 330 to the power of 3. Okay, and you can kind of see how this is working essentially. Okay, so what we're essentially doing is saying the amount of revolutions that have been spent in step 1 is 38.1%. So we're doing 38.1% of 1,100 to the power of 3. Then we're doing 14.3% of 330 to the power of 3. And then finally, we're doing 0.476, which is the highest value of revolutions are happening in the last 3 hours, multiplied by 805 to the power of 3. And then we put this all to the power of 1/3, and we will find that our F equivalent that we need to go into our catalog with, and we need to make sure that we have a bearing that can withstand that force, is going to be equal, if we calculate all the numbers, is going to be equal to 913 pound force. Okay, so we see that overall we would need a bearing that can withstand 913 pound force in order to satisfy this rolling 12-hour schedule, okay, with different loadings. So hopefully this makes sense. There's also some study problems that you can do, and if you have any questions, obviously let me know. Now, there's one more problem that we're going to do that should be much faster to do because we have a lot less. To do because a lot of the stuff is already done for us. But we're going to write it out, and we're going to do it in the same exact way. And this is another example problem that could be given on a typical exam for this module. So let me go copy this problem over as well. So we have this problem at the bottom here, and I'll copy it over and talk about it in a second. So here we have a situation where a skateboard is going to be pushed in the kick phase and not pushed in the coast phase. And in the kick phase, there's a 0.05 time fraction, or 5% of the time is used during the kick phase, and we have an average speed of 120 RPM during that time on our bearings. So our bearings are going to be these bearings right here. And then 95% of it is going to be at 60 RPM with a time fraction of 0.95. Now, in real life, that's not actually how a skateboard completely works, because we actually have a slightly different system for that to happen. But hopefully it'll make sense and we can work on this problem. And what we're looking for is an F equivalent to go find a bearing in a bearing catalog if we wanted to. So here we already are given the time fraction, so it does make our system a little bit easier. So the only thing we need to find is actually, since we already have TI, or the time fraction, we can say that we have to find LI, and I'm going to add it to our table here, and we can find FI. Okay, so Li would be 0.05 times 120, which would be 6. Okay, again, Li is an arbitrary number, it's just a number overall. And then 60 times 0.95 would be 57. And then if we look at it in terms of the fraction of the overall revolutions, we see that the fraction is actually 0.095 and 0.905. Again, has to add up to 1. So we can see that 90.5% of the revolutions come from coast, and 9.5% of the revolutions come from kick, which is different than the time fraction. Then we have FD in pound force. So we're assuming that we have a force desired, and that force desired is all radial, and we have an application factor given. So what we can do is we can say that we can find FE. FE is equal to FD, so we don't have to rewrite it. Okay, we're just given that FE is equal to FD. So we're not going to rewrite those numbers, but it would essentially be 35 and 45. And then we can do AF times FE just to have the values there already prepared. And that would be 42 and 45, since we have 1 and 1.5. So based on that, we can then say, well, let's solve our problem. We have that FEQ is going to be equal to a system of 0.095, which is your F for 1, times 42, which is your AFFE for 1. And then we have to put it to the power of something. Now, in the problem, it doesn't tell us if we have a ball or a roller bearing. So we can assume that we have a ball bearing, but you could also assume that you have a roller bearing. Okay, we're going to assume that we have a ball bearing, therefore we're going to use cubed as our value, and then we're going to have 0.905 times 45 to the power of 3, and we're going to put all of this to the power of 1/3, and we're going to solve the problem and find that this is equal to 44.7 pound force. So our C10, or our F equivalent, would be 44.7 pound force, assuming we would want 90% reliability. So if we think about it in a slightly different way, we could also say, well, we could also write that, for example, instead of having the time fraction, if someone hadn't given us a time fraction, but had given us that kick, for example, were 1 minute over a 20-minute period, and our coast would be 19 minutes over a 20-minute period, then we could simplify this and find that our time fraction would be equal to 0.05 over the total, and this would be 0.95, and solve the problem from there. Okay, and what we could write is then, well, instead of writing our time fraction directly, what we could have written too is that our Li in this case, so if we had left it as 1 and 19 minutes, our Li could be 120 revolutions, because we have 120 RPM, and our 19 minutes would be 19 times 60, So we would have 19 minutes times 60, would be equal to 1,140 revolutions. And the LI, the total for LI would have been 120 plus 1140 would be 1260. And we would find, in the same way as before, if we wanted to, we would have found that Fi, the fraction, can be done on a time fraction, but it can also be done on the actual time. Okay, so the fraction of speed times revolutions, we could then multiply the two together and divide by the total. So we'd have 120 revs over 1260. We would get 0.095 and 0.905. Okay, so hopefully this makes sense. And there are resources that out there, and your textbook has a little bit more information on this, but hopefully variable loading will be pretty easy to solve. Now, just one last thing to show you, and then we'll end this module fully, and we'll go into a next module in the next video. But just to show you, in the module 3 formula sheet, we have the equation available right here. So FEQ is equal to the sum of FI times AFI FEI to the power of A, all to the power of 1 over A. So we have everything available there for you to be able to solve. This equation we're not going to use, so this equation is not going to be used, but it would be the equation that you would use if you had a piecewise continuous system as opposed to a simple piecewise system. Okay, so if you had some more complex shapes, you would have to use an integral to find the area under the curve as opposed to just multiplying f times L essentially. Okay, so we're going to end this module here, and this concludes module 3. And in the next module, we're going to be looking at journal bearings and information on journal bearings. So we'll see you in the next video.